Hierarchy teaches you how memory systems work, and then module 12 hooks them up, okay, as components, basically is the way I've organized it. The book has a little bit different flow, but that's fine too. Okay, so memory devices. So learn the role of primary devices. So we talked about registers. We got a good handle on that. There's 32 registers, or maybe 100 in most processors. The next level up is cache memory, and then main memory. We'll distinguish between those. We're learning that there's 3 different device technologies. We talked about device technology. That means how do we build the transistors that implement the memory cell? There's different choices. There's static RAM. It's a certain type of transistor. Dynamic RAM, we use a capacitor. And there's other technologies that are non-volatile, which we'll explain. For memory systems, we need some policies that help us to find the data. Sounds simple, but usually when there's simple things, there's too many choices, right? So we'll look at some trade-offs, which gives us things to do, people to hire you to design these different ways, right? And using those, you'll be able to understand the performance trade-offs. Which type of strategy is best for which condition? Our 2 metrics, we always have some metrics as engineers. Metrics for memory systems, key ones, are hit rate, that's the percent of time that we find the data that we're looking for in the memory. And access time, this is a percentage of success, and this is a delay metric or latency metric. So where are we? We're following the blue region up here for instruction cache and data cache on the processor chip. So let's look at some hardware design techniques. So we've mentioned this abstraction model since the beginning of the class, and this is our last time to see it because now we're going to look inside the memory box in a lot more detail. So far in the class, we've been in the CPU box in terms of designing the functionality, the ALU, control path, and so forth. We're going to look inside memory now. So the process is that when a memory request occurs, what's a memory request? Well, we have certain instructions in MIPS. Anybody name me 2 instructions in MIPS that will load word and store word it is correct. Load word and store word and load byte, store byte are the only 2 instructions, either load and store, that the processor will go to memory to get data. So how does that work? In MIPS, as most processors, you specify a base address and an offset. Those are added together, and the data is loaded from memory into the CPU. So what happens? As I mentioned, now we're going to see the detail. CPU outputs the address bits over the address bus to DRAM as dynamic RAM. We'll explain that. And the control signals. We see some control signals here, and we'll explain more of those. For example, are we reading or writing? That's a control signal. And enable says the data is valid. What do we mean data is valid? We have some bits that are being transmitted over this bus. There's a fly time associated with that, but we're working at nanoscale resolution, right, and nanoseconds, right? So we have to make sure that the data is valid, and all 32 bits of the address bus, or all 32 bits of the data bus, are their proper 1 and 0, not a transient response, right, not still switching. That's when the enable occurs. DRAM receives this information, it looks up the information that's at that address, the data, sends it back. So here's an animation. We've seen this animation before, but maybe it's good just to refresh us. It's only 3 minutes. If we have audio, we can watch this from 220.
Hey, are you gonna play?
I don't know. Maybe. Yeah. All right. 220.
The access that is being processed by the CPU. Let's learn a little bit more about RAM by looking at how the CPU and RAM interact. For now, we'll remove the wires on the left and move the motherboard over to make room for the RAM chip. RAM consists of a list of addresses, and at each of those addresses is a piece of data. The CPU normally requests and processes each piece of data from RAM in order, one after the other. However, if the CPU is instructed to clear data out of order, it can do so. That is why it's called random access memory. The data can be accessed randomly if it needs to be, although normally it's accessed in order.
So question, I think I may have mentioned this before in this section, but we have random access memory and we have sequential access memory. What would be an example of a sequential access memory?
Tape drive.
Tape drive. Tape drive is, we have to get to the data at bit or byte or word or block 100, you have to go through 0 through 99 to get there. So that means you can only access data sequentially, not in a random sequence. All the memories we work with, such as this memory module, which I'll pass around again, is random access memory. It's a little bit of a misnomer, actually. So I'll just make an aside on this, which is good to keep in mind. Whether we say random access memory, and that has become known in the popular press, okay, and even the technical press, to mean that it's read-writable, okay? But actually, even read-only memory is random access, okay? So just be aware, random access means that I don't have to access all the words in between two adjacent references. ROM may also be random access. As a matter of fact, all the memories we use are random access. We tend to use the phrase RAM, like dynamic RAM, to mean that it's read-writable, okay? So this phrase itself means, okay, you have to get it from context, but if you buy a RAM chip, it means that it's probably volatile and you can update it. And I'll explain what these words mean. Updatable. Okay.
When the computer first starts running a program, it sends an address to RAM to begin retrieving that program. The RAM address just consists of a series of ones and zeros representing on and off wires. RAM doesn't do anything with that address, though, until the CPU also turns on the set or the enable wire. If the enable wire is turned on, RAM automatically sends whatever piece of data is at that address back to the CPU. That data is then processed by the CPU accordingly. Once the CPU has finished processing that piece of data, it then sends another address to RAM, turns on the enable wire, and gets the next piece of data from RAM. This process happens over and over again inside the computer. If the CPU needs to save data to RAM, it outputs an address, outputs some data, and then turns on the set wire. The RAM will then overwrite the data at that address with the new data.
That'd be store word.
What is that data inside RAM? Because it just looks like a bunch of ones and zeros. Well, it's made up of different things. Some of the most important pieces of data in RAM are the instructions. Instructions just tell the CPU to do different things.
Module 6, data encoding, instruction coding.
These are numbers that you might want to add together, compare, or simply process in some way. Another thing, and this is kind of weird, that is in the data is addresses. At particular memory addresses in RAM, the data itself is also an address. These addresses can be used for various things. For instance, if you want to output a number to an external device, you have to know the address of that particular device. Do you want to send data to the printer, or do you want to send it to the monitor, for instance? There are also letters stored in RAM. If you want to show some text on the screen, you would actually store it as a bunch of ones and zeros in RAM. Each letter is stored as a particular combination of ones and zeros according to a character code.
So you guys saw that in lab, so you guys are all up to date.
All right. That this is a lowercase a, and this is an uppercase G, for instance. So that's what's actually in the data inside RAM. Now let's go back to seeing the data as just a bunch of ones and zeros. And we'll now move the RAM chip into the RAM socket on the motherboard. We'll then group the RAM addresses and data together, pull the CPU out of the motherboard, and look at what's called the instruction set of the CPU. As we saw earlier.
So you guys can look at that if you like to prepare maybe for the final. It's a nice animation. We already did instruction encodings. So let's go forward with memories. And it's probably going to autoplay, right? So let me turn that off here. There we go. Okay. So let's drill down to the next level of detail. So I mentioned that we have memory of our abstraction. Let's look inside clear box view. Inside that abstraction, what's happening? So if you look inside the CPU chip, cache and registers are the two memory components. We said we had three, right? Cache, registers, main memory. So cache register within the CPU chip. Main memory is a separate module, which I'm passing around the room again. You guys can take a look at it, and it's what he showed on the screen over here on the right side. So I think you guys know what registers are. Cache, we have one or more levels of cache on the chip, and we'll explain what those are. They're organized hierarchically. And we have RAM. Okay, so RAM is outside the chip. So what is the physical view of this? And what we're going to get to in this module is, by the time we get to the end of the module, you'll be able to tell me how these buses are interfaced, how this device exchanges data here, what's the protocol, what's the size of this cache, how is this organized. That's what the module is about. So right now we're just starting out again, like Pink Floyd. We just give you the beginning of the song, and then we'll see it at the end. This box with all the numbers filled in. If you think physically, what am I, this is a functional diagram. Physically, what does it look like? Well, we know the DRAM or DDR slots. Okay, we'll explain what these acronyms are. That's what we're passing around the room is this module. So you plug this module in, right, to the board, and inside the module is the main memory. That's our memory map. So in this whole course, we've been talking about .text, .data. It's sitting inside this module that's going around the room right now. Those bits are stored in the main memory module. But for the CPU to access them, they have to be transferred into the chip. Once they're in the chip, they're going to be put into cache, and we'll explain what the concept is. But we can't fit everything inside the chip. We're only going to put inside the chip, this is the whole concept of cache, only the part of the program you're currently using. That turns out that's all we need. And then inside the CPU portion, there's also registers, right? Okay. This leads us to the concept of memory hierarchy. Memory hierarchy, if you ask me, is one of the most important and useful concepts in computer engineering after the stored program concept. Okay? On the electrical side, right, we have Kirchhoff's law, Ohm's law, we use them all the time. Memory hierarchy is something we use in almost every computer system. Why? It works great. It actually adds practically no cost, but increases performance significantly. And here's the concept. We have just a little bit of very fast memory, and we have a lot of very inexpensive memory. The point is that we're going to move programs or data between these different levels so that the processor has access to what it currently needs. Therefore, the fast memory doesn't have to be very large, and then therefore your system does not cost very much. Let's take a look. We say speed increases as we go up this hierarchy. What's typical times? The clock rate is 2 gigahertz. What's the memory access time of a register? 2 gigahertz clock. You got it. It has to be half a nanosecond. So registers, so what's the point? Registers have to be very fast. What's fast? Fast memory is for sure less than a nanosecond to access memory, very fast. Can we do that at low cost? Not really. Actually, if you look at a chip die, the register file is visible size area, even though it's only 32 words. Okay, it has to be very big transistors, a lot of drive, very fast. It has to be located right in the center of the core, okay, because it needs to be close to everything. And half a nanosecond, that's for 2 gigahertz. You want to go to 4 gigahertz? What's the memory access time of that register that you need to build? 22. Yeah, 250 pico. That's pretty fast. What's a typical gate delay? For like one AND gate, forget registers, right? Registers are sequential machines, right? They're even more complicated. What's a typical, we said we need 250 pico, right? So just a single gate is how many pico? I mentioned before a couple times. About 50, yeah, about 50. That's fast. And you had a question? Yeah, good.
When you're choosing memory,
yeah,
and comparing it to the CPU,
yeah,
to like avoid bottlenecking, would you want
yes
frequencies to match up, or what do you
So we want the system balanced, which we had a diagram of that before. You're exactly right. When we look at a few different technologies, we're going to come back to this in module 12, the next module. Yeah. It turns out that's really what matters to the system. So we have speed increasing as we go up the hierarchy, and we have capacity increasing as we go down. Okay. Why would we say here it's infinite capacity?
Because you can keep adding more
You can keep adding more, right? You can put as many thumb drives as you want in your laptop, right? And it gives you like the illusion of, yeah, okay. So, what's the takeaway? Speed increases, this is the cool thing, about 10 times per level. This is just a rough numbers, but this is 0.5 nanoseconds, and if you buy DRAM, it's about 50. You can Google it right now if you have your laptop. What about capacities? How are these changing as we go from level to level? Anybody see the trend? Tenfold? 2 to the 10. Yeah, 2 to the 10. Yeah, about a factor of 1,000. 2 to the 10 is 1024. Okay. So yeah, 2 to the 10, yes. So speed increases 10 times per level, and this is about 1,000 times decimal, right? Or 1024. So we're going to concentrate in this module, okay, actually in the course, on these two areas, and we're going to start here in cache. So we have memory systems. Memory has two opposing properties, and I think anybody who's studied for a test, right, it's the same thing. If you need to know a lot of information, you may not be that fast at retrieving it. If someone only asks you to remember one or two things, you can find that data quickly. So we have these expressions that, little sayings, right? Large memories are slow, fast memories are small. So we want to create a memory system that has, at least to the processor's point of view, because the processor works with the memory and the memory actually serves the processor, right, the request, to be giving the illusion of being large, inexpensive and fast all at the same time. Well, these are opposing properties, right? You know, you want a sports car, but you want it to cost hardly anything, and you want to get whatever miles per gallon or whatever, Tesla, right? But then the cost goes. So how do we get all these things at once? We use two properties. One, as I mentioned, is memory hierarchy. It's a basic property of computer engineering, just like Kirchhoff's law is for electrical. Hierarchy says we can leverage locality, it's explained on the next page, which is the computer science property that we use as engineers to make something that achieves all these objectives at one time. Bless you. We also use parallelism. We know what this is, right? Multiple bits on the channel. So if we state this in terms of metrics, we want to achieve an access time that's low. What's low? Well, ideally close to registers. All right. But we want an average cost of bit in the entire computer system to be close to that of secondary, if we're very lucky, tertiary storage. Okay. We have the new Intel Crosspoint, which is a PCM-based technology. But these are opposing things. Okay. So we're going to show you how we use these two together to achieve all the goals most of the time. So here's memory hierarchy using principal locality. Here's the chip. First two levels plus registers are inside the processor chip, DRAM outside. Cost, this is the highest per bit, lowest per bit. Speed, clock cycles, typical numbers. Okay. What's the difference here? This is saying if your clock is 2 gigahertz, then it's going to be 0.5 nanoseconds per access. So there you go. Okay, but this is the trend. Okay. So here's some real numbers. It's actually from the board that replaced the one I passed around before. So when I bought the new board, I just ran this to see what the heck's going on here, and this was what speed processor was this right here? How many gigahertz? 3.5 gigahertz, awesome, okay. And here you can see cache capacities, and you can see the bandwidth, what is that unit? Mega what? Megabytes per second transfer, okay. And the capacity, okay, for some typical numbers. What do we learn here, right? What I said, the L2, L1, L2, right? You can see we had 32 registers, and then L1 we had about 1,000 times. Yeah, it's, roughly. We have 32K bytes, okay? Not words, but bytes in L1 cache and so forth. Okay. So locality. Locality is the computer science property we use as engineers to make a memory system work. The idea is we can only use a small part of the program at any time, something called 90-10 rule. Okay, so what's the 90-10 rule in life, if you're a business major or whatever? Yeah, go ahead. Jack.
10% of your efforts equate to 90%.
Exactly right.
Your
profit. So this is every discipline, this kind of behavior, and even in life and whatever, right? I mean, it's true. So if you're a business major, they tell you, if you're marketing or let's say sales, 90% of your sales come from 10% of your customers. Or if you're a company, 90% of your profits come from 10% of your product line. Or in our case, when we execute a program, where do we spend 90% of the time? What type of structure when we're executing code, machine code? Loops. So, before we see the answer, which is the next 2 weeks, which part of the program do we want to put in L1 cache? What part of the program do we want to put in, since we're spending 90% of the time in loops, and loops tend to be kind of compact, where will we store loops? Will we store them back out in tertiary on the thumb drive? No, where do you put it? L1. There you go. Does L1 have to be that big? No, because 90% of the time you're in the loop. As long as the L1's big enough to hold the loop, 90% of the time you think you're running at maximum speed. That's the idea. Okay, so we mentioned this not only as a code, loops, but also scalars and things we always, I is I plus plus, next I, same variables coming up. If we generalize this, we can say that memory access is not uniform. If I make a distribution, a scatter plot, scatter graph, right? Of all the memory addresses and how many times they're accessed over time, there's certain ones that are used more. Wouldn't it be wonderful if we can put those in the fast memory? That's what a cache does. We said, how do you find out what's used a lot and what's not used a lot? That's the cache's job, the memory controller. And when there's good heuristics, what's the word heuristic? Anybody know? SAT majors. Heuristic. It's a guess. It's like something that works well most of the time.
Processor.
Okay. Heuristic? What does it say? Definition. Enabling a person to discover or learn something for themselves. A heuristic method is simply a heuristic technique in computer science. It's designed for optimization that's right most of the time, but not perfect. So what we're going to do is we're going to try to identify what's good to put close to the processor. We don't make it perfect, but that's the hit rate. Percent of the time that decision was correct. So this is an important property of computers, programs to reference here, locality of reference or locality. Sometimes you use this word, sometimes we use this phrase. Okay, let's see that there's two types of locality. Again, spatial and temporal. Just like I said, you're going to see this over and over again. Time versus space trade-offs. Everybody is good? Time versus space trade-offs. So here's temporal as a time version of locality. Can anybody look at this? The explanation is kind of there, but it's nice we have active learning. Why would this be an example of temporal locality? I'll give you a second to look at it. Yeah, raise your hand. Was it Miguel or who was it? No, Neil.
It would store the address of T1 every time, so it was run at the register level all the time.
Yes. So in this particular case, you can see that when we go through this loop many times, we don't know how many, it's based on, right? This is actually a BLE to get out of it, right? Okay, but in any case, we don't adjust the address. It's the same address time and time and time and time again. If that address happens to be in cache, I don't have to wait for slow memory to update that value because it's in cache. It's an example of temporal locality. So temporal locality leverages, in words, right? Leverages keeping the most recently accessed data close to the processor. That's temporal locality, okay? In other words, I just used something I'm going to keep it out. So I have a good example. So let me just give you these two first, technical, and then I'll give you the everyday analogy. So we have spatial locality. Spatial locality is locality over space. That says, the easiest way to see this is instruction version and the data version. In the data version, if I'm accessing address X, then we see the distribution probability that it's more probable I'm going to access an address near to X. For example, we've already did so many of these cases where we're traversing memory, for example, a string or an array variable. We get a sub I, then a sub I plus 1, a sub I plus 2. If I access a sub I in the current iteration, it's more likely I access a sub I plus 1 or I minus 1 in the next iteration than just any other random address. You're going to say, well, it's not always true. Right, it's a heuristic. Okay, you know, what is a heuristic? Well, when I see this behavior, this likely happens. Is there a causality? Not necessarily, but it's correlated. So we can use that to our advantage. What can we do? We can transport blocks of contiguous words between processor and memory. Back to SAT, contiguous, not continuous. Contiguous, and that's a hint. What's the difference between continuous and contiguous?
Contiguous means they're touching.
Good.
It means they're touching. Continuous.
Contiguous, they're flanked, they're adjacent, and you're exactly correct. So contiguous is for space, all right, these analogies, the double colon thing, right, is the same as continuous is for time. Continuous time means it's one after the other, sequentially, chronologically, one event after the other. Contiguous says, you know, the houses are contiguous on the street, right? There's one after another. Okay. So what we're going to do here is we're going to move blocks of not just one word. When we access, this is very key, when we access a word of memory, we're going to fetch that word, but also we're going to fetch a block around it. Why in the heck would you want to do that? Because there's a
high chance that the ones that are right next to them are going to be referenced soon anyway?
There's a very high chance, due to spatial locality, that we're going to reference something around it nearby. Is that going to happen 100% of the time? No. But if it happens, I don't know, even 90% of the time, that means 9 out of your 10 accesses are sped up. So you don't have to go to slow memory again and again and again and again. So let me give you an example of both of these and we'll answer your question. So example, everyday analogy, I'll give you some accumulated over time here, of temporal locality is, you say you're in the kitchen, you're working with something, you're cooking something, you know, you leave it out, right? You just chop this thing and you have to do something else, you leave it on the counter. The counter is your cache or maybe even your register, right? Okay, it's data that you can get to quickly. It's nearby, okay? You don't do something and then once you're done with that little step, maybe wash it and put it away back in the shelf, which is long-term or maybe medium secondary storage. So temporal locality is something I'm using. Or example would be a book on, you know, you have books on your bookshelf. Okay, I don't use too many books anymore, but I have a few in my office, and they're on the shelf. That's like secondary storage. Whatever I'm reading comes down to my desktop, right? And then if I look at something, you know, I might want to keep it out. And what you do, right? We all do this, right? Just push it to the side, and that's temporal locality. Why? Because you might use it again. What's an example of spatial locality? So example of spatial locality that we see very regularly, okay, let's say I have things in storage, like public storage, right? You rent one of those things. When you go there, you just don't pick up one thing, right? Because it's too much expense, right? Because you got to check in at the gate and those keys and nothing works and all that stuff, right? So what do you do when you go there? You come back with just one thing? No, you come back. So you go fishing, right? So you tackle box, you know, oh, but you know what? I'm gonna get my my tennis rack because it's getting warm now, or cold now, I guess. It's getting nice out, so I'm gonna get what? Spatial locality, right? Why? Because there's a big expense to go fetch from slow memory. What's slow memory in this case? Public storage. Okay. Why? Why don't you just keep it in your closet? Well, it's fast, and so it's expensive, you know. We don't have a lot of storage in your closet, but you may not have enough to store all your stuff, so you put it in slow. This is the same concept. Any other questions? You good? Eric? Is it good?
I did.
Yeah.
Where are these extra instructions? Are they stored in cache or
Good question. So these instructions that we're executing?
the extra, like when you say you take a block and you
Yeah.
put it into, where is that extra? Where is that stored in the CPU?
Good question. So we're going to see this on the subsequent slides, is that the entire program is in the .text over here. And then what we're going to do is move some part of it. That's for us to design. It's usually about 1K words. 1K words is a typical transfer size between these levels. So we move 1,000 instructions over, and then we can execute anywhere in that 1,000. If you do a branch or a jump, remember we did a address calculation? Remember that 40,000 and everybody was having questions on that? If you go more than 1,000, then you got to fetch another block. But if you are within that 1,000, it's already in cache, and probably level 1 cache. So what this is it's public storage, this is your garage, and this is your closet, right? And it gets to be, not so much in Florida, but up north, right? It was a pain, right? And too many years ago, but long-term memory, right? It gets to be cold season, right? And then you get those winter coats out, and then you put them back, and then because they're different, you're in a different locality of execution, temperature locality. So we mentioned this property. We've seen a couple examples. Here's another diagram, and this is getting to Mr. Smithson's point, is to transfer information between CPU and cache. We don't have too much expense as fast, so we can transfer individual word at a time. But between cache and main memory, this interface is slow. It's actually on the circuit board. Where's this interface? CPU and cache actually is on the chip, right? On the processor chip. Well, here we have to go over this slow, okay? So we may want to transfer more than one word at a time if we're spending the time to go there. Anybody speak French? Is a cacher is a French word to hide, actually. So what we're doing literally is hiding a little piece of the program, some subset of instructions in fast memory for future reference. You're caching it away. It's your instruction cache or data cache. That's literally what it means. So if we look at this, the speed is increasing as we get close to the CPU, and it gets slower as we go away. Can anybody see the pyramid here? It's just drawn at an angle, right? See? What do I mean by pyramid? We have temporal and spatial aspects, time and space complexity. Tell me about this pyramid. Where's the right? The fastest up here. What about capacity? Registers inside here, right? Yeah, all the capacity is down here. Okay. So let's go to the next level and make it real and start to do this block word transfer, and then we're going to solve some problems, calculate hit rate. So here's our procedure. First we're going to see if a word, okay, which is a red box here, is referenced by the processor via its byte address in main memory. Memory is always byte address, so we're going to add the addresses in a second, but let's get the flow. We first have to see, is that information already in cache? So what the processor is going to do is look in cache and sees if it finds this particular information it's looking for, which is this one word. It turns out cache is organized into units called lines. A line is like a pallet of data, or a box or a suitcase when you go to public storage, right? You come back with more than one thing that was in a container. The size of the container is called a line, okay? It's actually a block. So it's block when we're in main memory, when you're in public storage. It's the same size container when you get home, but to distinguish is the container at public storage or at home, we use the words block and line. Block is the main memory container. Line is the same container after it's been moved into main memory. What's the difference between block and line? We're going to see. I make it like very getting your attention, because people are always missing this. There's no point to miss points. Block and line are always equal. Let me say it again. Block size and line size are always equal. If there's a block of 8 words, it means the line size is 8 words. If this is the 1, 2, 3, 4, 5, 6th word within that block, it's going to be the 6th word within that line after you move it back. So you're going to say, well, why do you need these 2 different words? It's just how it's called, but it also helps us to tell us when it's a line that's been moved. If it's a block, it's in memory. I try to keep consistent with that. The author is a little bit loose on the terminology, but just keep in mind that that's the idea. So how this works is a processor wants to access this word, like, what do you mean? Load word, right? Load word. Load word has a base and offset. You add them together, it goes to an address. They're added. That address was resolved to this particular word of memory. Well, if that word of memory is in cache, it's a hit. We find the data there, we just forward it immediately to the processor. No worries. What happens if you don't find it in cache? All right? Same thing, you go to your closet, the thing's not there, and then what do you gotta do? Gotta go main memory. Public storage. So what are we gonna do? Are we gonna just bring this one word over? No, a whole block. Okay. So the analogy, public storage, warehouse distribution, okay, transporting a signal item is not worth the overhead. It's better to transport a pallet at a time, right? Okay, another analogy, right? You go into Publix. It's down the street here or wherever, downtown Orlando, wherever you live, real estate's expensive. Where's warehouse? In Florida here. We drive out to Tampa, right? What do you see? Warehouses. Publix, right? This IKEA, right? Huge where? What city? Nobody? Nobody's driven to the Clearwater and goes to the beach anymore? What is it? You guys have to get out more. I don't know. We have Wednesday, right? So Wednesday, go to Clearwater, go to the beach. It'll be crowded. But what do you see between here and there? Besides orange groves and stuff, and a lot of distribution center. Remember Publix is off on the side there? Did I Google it? You know what I'm talking about, right?
It's in Lakeland, right?
That's it. Why isn't, that's what I wanted you to say. Why is it in Lakeland? Exactly. Real estate's cheap. This is the cheap real estate, right? What's the problem with it? It's far away. So, when you go to Publix, and what cereal do you like? You don't eat cereal, nobody does, right? Because it's carbs, right? Cashew lean, okay, so it's healthy. You go there and your box of cashew lean's not there, what happens? Do they send a truck out to Lakeland, bring you a box? They come back with a pallet. It's block transfer. Why? Because the expense is too long, it's too slow, right? To make it worth it to get one box, you move a whole box at a time. We do the same thing with bits. The container is called block, it gets moved in as a line. This is the data that was referenced. Well, we only wanted one box of cashew lean, but a pallet came back. Well, that's how it works. Because of locality. Okay. Here's another example of locality, right? This is, nobody can get you guys awake. See, don't worry, I'm not pointing anybody. Yeah, that's fine. You're actually viewing. This is a true story, okay? So when I worked for IBM, we had a client, okay? This is actually the name of the client. They were in Tennessee, Acme Boot Company, which we're not so much into Western wear here, but Colorado, right? You wear boots and stuff. It's really, you do. You might have been to Denver Airport, right? Denver Airport. You'll see people wearing boots and stuff. That's like no. So this company was called Acme Boot. They made Justin boots, if people know that brand. But they had a big distribution center, right? And the whole thing was industrial engineering a little bit, but we had to make a fly-by-wire robot, and this was a big deal because it was so many years ago. But how do you organize the data for spatial locality, right? And I started reading these papers and said, people actually study this. It's very interesting, right? And this is why it's always, when you go to the store, they're always changing these things up, right? Because they want to promote certain products and stuff, but they put stuff together, okay? So here's a funny story to wake you guys up, just make it interesting, right? It was one guy came and talked to us, and they worked for Kirkland, and the 7-Eleven was their client, and they said they just had this breakthrough that they wanted to put diapers and beer on the same end cap. And why? But why did they want to do that? I mean, babies can't drink beer, or they shouldn't, right? Or if you're wearing diapers, then it's probably time to quit drinking. But what? Why put them together?
Babies don't want buying diapers.
Was it? Yeah, you're right. Go ahead and say again.
I mean, it's probably the dad going and buying the diaper.
That's exactly what they said, and I'm just, I won't put any genders attached to it, but someone's told to go to the store, and it's a Sunday football, whatever. Anybody can watch football, right? There's no gender associated with it. And then they're told to go there, and they, guess what? They're going to grab some beer because that's what. And it's don't forget the diapers. And they found that when they put those two together on the same end cap, their sales went up. It's an example of locality, actually, right? Locality. So here's our read operation flowchart in detail. You can see when we're referencing data from the CPU that there's a couple of choices here, and now we're going to see this cache lean come back, and there's a couple choices based on how good your grocer is, right? You know, talk to your grocer. I'm a grocer, but we'll talk about that. So here, I'm referencing data from the CPU. We're going to see if the block that the requested address, right? This is we use the word read address is actually after we've added base and offset together. So that's the so-called effective address. We want to read from is a memory address, is a byte address. Well, there's two choices. Is it in the cache? If the answer is yes, is the easier case, then we just forward that data. It's the same as the previous as a flowchart. If not, we've got to go to main memory to get it. We're going to move a block back at a time, not a word, but a block back. But now we've got a choice, okay? So we call this either load through or read through. They're two words for the same thing, okay? But the idea here is that we have two choices. We can either load main memory block into the cache line, which we see happening here is this gold line. See, we try to keep it UCF. We do, actually. I did all these slides for this. I'm serious. And then after the block comes back, that's one choice. Or we can deliver this word directly to the CPU. So you're in the store, and there's no cache lean. And this is a new thing at Publix, right? It seems like they're trying to be like extra friendly or something, I guess. I don't know. Have you noticed this too? How you doing and all this? You're just like there, right? You don't want to shop, right? It's like you've been at work all day, you want to talk to these. Well, you just say hi, right? But then, okay, but actually it's handy because it's like there's nothing on the shelf. You're like, hey, I just noticed I don't have any of this cache lean here. Can you help me? So the guy's going to do what? It's not in the cache. It's not on the shelf. He goes in the back. Okay. When he comes back with a pallet, right? Because that's how it's delivered. There's two choices, right? He can either hand you the box you wanted, or he can start loading the shelf. Which of the two is which? We call this, if he hands you the box, we call it load through. He starts loading the shelf. So if he's rude, that means that establishment does not support read through or load through. What does it mean? They had to go to the back room and get the data, and it came back with the whole pallet, a whole block. But because we know the processor is waiting for that data, the customer is waiting for his cache lean, they can't, because he's nice, right? Because they're so into service, which actually they're pretty good about it. They're going to hand you that box right away. That's load through. Processor can do the same thing. So we have this choice. You can either have read through or not have it. Okay. Most CPU systems have load through. So when we have a miss, we'll start to use these words. When we have a miss on cache, no cache lean on the shelf, we go fetch a block, bring it there. If we have load through, it's immediately forwarded to the processor without waiting to load the entire line on the shelf. Some more terminology. We talked about hit and miss. So let's define those more formally, then we do calculation. The hit time is a portion of memory access that are found in the cache. What percentage of time you go to the store is your cache lean there? Okay, well, pretty good actually, then it's a good store. You have a high hit rate, right? We can calculate that. This is the time to access the cache, is the hit time, right? But we also have the miss time, which would be my expected time to get my cereal. 99% of the time it's on the shelf. It only took 5 seconds. But once a year, twice a year, they have to go in the back to get it. On average, it's going to be 0.99 times 5 seconds plus 0.01 times 3 minutes. That was the miss rate, was the time we did not find the data Fraction of access is not found in the memory hierarchy each level. So we have a miss rate for L1 cache, have a miss rate for L2 cache, L3. And these things are like a layer cake, right? You start at the top and then you go to the next layer, the next layer, the next layer. If you don't find it here, you look in the next and the next and the next and the next and the next. All right? You go to Publix, it's not on the shelf, they look in the back. They come back, you know what? We're totally out. Got to go to Lakeland. So this is a total time, right? In general, right, the time that when we find the data in the level closest to the processor, it's usually faster than having to pay the penalty to get the data. And the point is it's much less. So now we're ready to try an example. Here's the last analogy, and it just will help in this next example, which is a little bit heavy. So just, if you don't like analogies, you don't have to listen, but I think it's useful. So we're going to show how cache works. Let me show you where we're headed here. We're going to show how these blocks of main memory are mapped to a smaller cache. Actually, this is not even whole memory because it's actually 1,000 times more, but we're going to show you just a small example. But there's a lot of choices for this. And how it works is we're going to use the address of the blocks or the words in memory. It gets a little complicated, so it helps if you have something to think about first. It's based on my experience. So what works for me in my mind is I always think of this example as a coat check at an event. So what happens, okay? You want to go to a, I don't know, fancy restaurant or a theater or something. Maybe a restaurant's not big enough, but or you go to a supermarket in Europe and everybody carries their bag around because you ride the public transportation, right? But then when you get inside the store, what do? You have your bag, right? They don't want you shoplifting, so what do?
Put it in the front.
They put it in the front and they give you a little tag, right? And you come back with that. That's what cache does with the data. But we have to retrieve that data later. So here's the idea: is coat check. We're going to exchange our jacket or data with a paper tag with a unique number. The tag has two halves. One is a stub you keep, the other is attached to the jacket. Let's say you're checking in your jacket. The attendant, which is a cache controller, looks at the last digit to determine the bin to place your jacket, assuming there's 10 bins. So let's try this simple example. So you go to some fancy place, right? Fancy restaurant, fancy place. And there's the attendant. And in the back he has bins. This is bin number 9, bin number 0. We're going to start numbering from 0 just to make it easy. And you walk up with your jacket. You see, I'm a terrible artist here, right? So there's a jacket. Okay. So you're going to give your jacket to the attendant. He's going to give you a tag back, and this tag has a couple halves too. He's going to keep half, or it's usually perforated, right? There's a paper tag. But it's going to have a number on it, okay? Let's say 2105, okay? And it usually has the same number twice, and he gives you a half, and he keeps half over here. What does he do with your jacket? Well, one way to see if it's his first day on the job, we've seen these guys, right? They just take your jacket and they throw it in a pile. What's the problem, though? You go to leave. You hand him back your part of the tag, 2105. What does he do? Starts looking through this whole pile, right? So then the second week on the job, what he does, he has 9 bins. He's getting better, right? What does he do? Well, one way to do this is use this lower digit to tell which bin to put the jacket in. So this means bin number 5. I'm going to look, this is just an analogy. I'm looking, but actually this is how the memory works. Look in bin number 5, where to store this in the cache, okay? And then they'll tell me where to retrieve it. So later when we go to retrieve the jacket, we're going to hand back this tag, okay, to the attendant, or half of the tag. And the attendant is again going to look at the last digit and then know that our jacket is somewhere in this bin. This helps us find the data more quickly than keeping this unorganized. Now this is only 10 bins. We can have as many bins as we want. Okay, so the point is that we see there's many items to manage, which means a large memory space. A lot of people are going to come want to check their jacket. We have a limited amount of space to store this in as the cache. We need a way of organizing this so we can retrieve the data quickly. One way is using this tag Does anybody think of memory address, how this relates to? I just said the answer. This relates to the address, right? I was going to say address or data, but this is a memory address, right? We're going to use what? The lower bits, these are lower decimal digits. We can use lower bits of the address to tell us what bin. What do we think we call bins in the memory? Cache lines. Those are bins. We're going to look at the address bits and figure out which cache line. Now here's the thing. Decimal over here, we have one digit gives us 10 choices. It's like, you know, for human graspability is like, okay. What if I give you one binary digit? How many choices do you have? Just 2. So if you want to have like pretty good organization, is 1 bit enough to tell you which bin? No. Okay. So our tags are always more than 1 bit. But it's the same as decimal. So you guys totally know how cache works. The funny thing is once we put bits, it's like a mental block every single time. So don't forget this analogy, okay? It's something you already know. The way cache works is completely something you already know. We're going to take this paper tag and replace it with voltage levels on the address bus. We're going to take the lower decimal digit and replace it with, well, maybe a handful of bits. Is that it? That's it. Who is this guy? This becomes the cache controller. Okay. What are these bins? Cache lines. What's out here is all blocks of main memory. They're maybe reference is what's data is a jacket. This is data, it's address. Let's take a look. It's answering these questions, and let's put some numbers to it. You have 8 cache lines. It's like 8 bins. You have 1 word per block. We're going to start out easy. So we're not transferring a pallet at a time. Our pallet is just 1. Our container only holds 1 word. We'll make it more complicated on the next slide. So direct map strategy, and we have initial state. Now we're looking inside the cache. So what you see here is cache memory. We're back to having these different fields. All right, we always do this. So there's different bits inside cache, and they'll have different meanings, and we'll talk about this. Okay, we'll just start you off to say that this is empty, which means it may contain some junk data, but we're not going to care about that. What we just do is look at this V bit is a valid bit. Either the memory is valid, or this line is valid or not. Okay, and here's our index is actually the address. You see it's 0 through 7. Yeah, it's the same as this. It's just written this way. Okay. So we're going to get back to these in a minute, but we're using this log property to tell us what? Well, in this case, let's say, same as this. We had 32 words in memory. How many bits on the address? How many bits of address? 5, right? There's 5 bits of address to give us 32 distinct memory locations or addresses. So the point of this operation, this is a quiz question for sure. I don't mind telling you because it's some realistic to know, understand how cache works, is calculating the hit rate. We always give you a list of CPU reference addresses. So in this little tiny example, there's 32 memory addresses from 0 to 31 inclusive, and the processor did a load word of 22, a load word of 26, maybe a store word at 22, a load word, blah, 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 in that order. Someone wants to know, what's the hit rate? How do we do it? Well, what you're going to do is map out cache and look at each axis. Is the data present or not? Data is present is a hit. If it's not present, it's a miss, and you're going to add these up. So how do we do that? Well, first of all, it's given, right, that we're accessing